We shall now talk about finite temperatures, because the experiments for condensed matter systems are always done at finite temperature, and an important goal of the physics that we are doing is to explain experiments or experimental data, and for that we need to go to finite temperatures. So far we have been talking about zero temperature Green's function, and now we shall talk about finite temperature Green's functions. So, what happens at finite temperature is that all quantities get weighted by the factor. So, by exponential minus beta e, where beta equal to 1 over kT, which is called as the inverse temperature, and k is the k with a subscript b is called as a Boltzmann constant. So, now what happens to the operators at finite temperatures? So, which means that the operators have to be weighted by this operator, where H is the Hamiltonian of the system. So, now so at finite temperatures, the operators that we need to write down the Green's function, they have to be weighted by this quantity or the weighting factor, which is exponential minus beta H, beta being the inverse temperature or 1 over kT. H is the Hamiltonian for the system. So, we write down a Green's function as so Green's function we will write down later, but it is written down as the trace of exponential beta H, Ck sigma t and Ck sigma t prime divided by trace of exponential minus beta H. So, this is the form of the Green's function, and the trace implies the Tr is actually the trace, which implies that we have to take the trace over the complete set of states n, and the operators, this is pretty much we are still at zero temperature. So, the operators are written as exponential I h t, Ck sigma 0 and exponential minus I h t, h being the h 0 plus h prime. Right. So, this we have seen, and so H prime now appears at two places. So, you remember that we have done a perturbation theory with in powers of H prime. Now, H prime is occurring at these plus minus I h t. We have dropped a h cross the Planck's constant, and it also appears at exponential minus beta h. So, this appears at both places. We were writing a curly h, does not matter. So, H prime appears at both these places. So, the perturbative expansion in terms of H prime was earlier included in this term, and should we now again do a perturbation expansion in terms of H prime with this? So, that is the question. Now, the answer to this question was given by Matsubara in the year 1955, in which he realized that beta equal to 1 over kT can be considered as complex time. So, if you consider this as complex time, this beta, then these two factors which are written here and here, they can be combined together. And so, basically if they can be combined together, then we can do a single perturbation theory with respect to H prime and can write down the complete Green's function or the full Green's function in terms of that. But what finally was done is exactly the opposite. Time is regarded or treated as complex temperature. This is an important concept in the finite temperature calculations that we will see henceforth. Another motivation of the Matsubara formalism, so we henceforth we call this as the Matsubara formalism, is that the occupation numbers for bosons, the occupation numbers which are the distribution. So, these are bosons and fermions, and this you know that this is written as exponential 1 divided by exponential beta h cross omega q minus 1, where omega q are the boson energies, and this is written as exponential beta epsilon k plus 1, and where epsilon k's are the energies. So, these are the occupation numbers. Now, these occupation numbers can be expanded in a series, and let us call this one as NF. Let us call this as NF, and let us call this one as NB. So, NF is written as, which is as we have written earlier, it is plus 1. This is written as a series half plus 1 over beta sum over n equal to minus infinity to plus infinity, and this is 1 divided by 2n plus 1 I pi by beta minus xi k, and the NB for the energies omega q, which as we have written it down minus 1, this is equal to a minus half plus a 1 by beta n equal to minus infinity plus infinity divided by 2 pi n I by beta minus omega q, or we can keep this h cross here, or we can drop it later. Now, these are the expressions for the occupation densities or the occupation numbers for the fermions or bosons. We will not provide a proof for that, a rigorous proof for that, but definitely we will tell you that it looks like that there are poles or singularities. If you are familiar with the complex analysis or the complex integration, these are called as the poles. So, there are poles at odd multiples of I pi by beta, and these have poles at even multiples of pi over beta. This we will prove, and we simply say that this comes from a theorem, and the theorem states that any meromorphic functions, please see the definition of meromorphic functions. May be expanded as a summation over its poles and residues at the poles. Let me box this thing. I am simply taking the statement and using it. To know more about this, you can look at a complex analysis book by Churchill. So what it says is that the boson occupation function, so NB has poles at even multiples of pi over beta along the imaginary axis, and so let's NF, it has poles at odd multiples of pi over beta, but which lie on the imaginary axis. Okay. So these are even things are 2n pi I by beta, and this is 2n plus 1 pi I by beta. So both the summations, it is apparent that can be written as as 1 sum over n, 1 divided by I omega n minus omega q, this is for bosons, and this is again a sum over n I omega n minus psi k, this is for, or psi q does not matter, I mean the momentum index does not matter, for fermions. So this is for bosons and these are for fermions. For fermions they are odd integers of pi over beta, and for bosons they are even integers of pi over beta. Now it is interesting to note that this form, either of the forms, they correspond to a non-interacting Green's function. Function is of the form 1 divided by I omega n minus psi k, and this non-interacting Green's function is called as the Matsubara Green's function. Matsubara is a Japanese physicist. So, now in the Matsubara formalism, as we have said, that time is a complex quantity and it's actually written as, it's actually an imaginary quantity. If you, it's a, and which is written as tau equal to I t, and the Green's functions, these Green's functions, the Matsubara Green's functions, functions are functions of tau and bounded between minus beta to beta, to plus beta. So, that is the range of tau for the Matsubara Green's functions, which are, so tau is nothing but the time, but it is just that it is a complex time, and these Green's functions are functions of these tau bounded between minus beta to plus beta. Now, let us take any function which is a function of tau and bounded between these values minus beta and plus beta. We can always do a Fourier series. So, take an arbitrary function f tau, which can be expanded in Fourier series of the form so f of tau equal to half of a 0 plus n equal to 1 to infinity. We have a n cosine n pi tau over beta and plus b n sine n pi tau over beta. So, where the coefficients a n and b n are defined by a n equal to 1 over beta minus beta to plus beta, as we said that is bounded by minus beta and plus beta. So, this is f of tau and a cosine of n pi tau over beta, whereas the b n is exactly the same thing, but with the sine term f of tau and a sine n pi tau over beta. Look at Afken mathematical physics book or Krzyzig for information on these Fourier series. So, in a compact notation we can write f of I omega n, this is equal to half of beta a n plus I b n. So, this is the rather the this is f as a function of these frequencies that we had talked about, and which can be obtained from the Fourier transform of f tau in the following fashion. So, f tau is related to the f I omega n as n equal to minus infinity to plus infinity exponential minus I n pi tau by beta f of I omega n, such that our f of I omega n is nothing but it is equal to half of minus beta to plus beta d tau f of tau exponential I pi n tau over beta. So, these are the properties of these functions. We shall later show that these functions are nothing but the Green's function, the Matsubara Green's function that we are going to talk about. And as said earlier, that these functions are needed in order to have the experimental quantities which are always done at finite temperatures. So, there are further simplifications possible, and for bosons the simplifications are like this, that we have an additional property which is equal to f tau equal to f tau by beta, tau plus beta for minus beta to be in the range for tau to be in the range minus beta and 0, and so this is a sort of periodicity of the function tau. We are going to show that, and for fermions we are we have an antisymmetric situation in which we so this is again in the limit tau to be between minus beta and 0, and let us show this for bosons. So, f of I omega n equal to half of 0 to beta d tau. I am splitting the minus beta to plus beta integral from 0 to beta and minus beta to 0. So, this is the first term f tau and exponential I pi n tau over beta, and plus a minus beta to 0 d tau f tau exponential I pi n tau over beta. And now, if we change the variables in this term, if we change variable from tau to tau plus beta, then I get f of I omega n to be half of 1 plus exponential I n pi from 0 to beta d tau. So, both of them can be combined to write it in this thing. One should check this, n pi tau over beta. So, because of this first factor here, f of I omega n equal to 0 for n to be odd. Thus, for bosons we can write it as f of I omega n equal to 0 to beta d tau exponential I omega n tau f of tau, and for omega n to be even number, because for odd it is equal to 0. So, 2 n pi by beta, and similarly your f tau becomes equal to 1 over beta sum over n, but now n is denotes only odd only even integers, and this is minus I omega n tau. N integer means the omega n will correspond to even factors, or rather even multiples of pi over beta. That is what. So, n is restricted in that sense, f of I omega n. So, this is for fermions. So, we have used this property which is because the tau going to tau plus beta, then we have used that f tau of beta equal to f tau and have written down this second term here, and this second term becomes equal to 0 if n is equal to odd, and that is why the bosonic frequencies are even multiples of pi over beta. Let us see this for fermions. For fermions, we have this odd property, and then I will again split up the sum or rather the integral into two terms, which is half 1 minus exponential I n pi. Again I will do the same trick of writing down the minus beta over 0 to change the variable from tau to tau plus beta and use the antisymmetric property of f of tau with respect to f tau plus beta, and this is equal to, so d tau f of tau exponential I n pi tau over beta. All right. So, now it says that f of I omega n equal to 0 if n is even. For n to be odd, we have f I omega n. So, we have omega n to have only odd values of pi over beta. So, this is going to be 0 to beta d tau exponential I omega n tau f of tau, and f of tau, the Fourier transform of that is equal to 1 over beta sum over n exponential minus I omega n tau f over I omega n, and for these things omega n equal to 2 n plus 1 pi over beta. Okay. So, these are things that we have learned. Now, we have written down that f is an arbitrary function, but however, that arbitrary function having some symmetry, it tells us that there are these the frequencies for fermions and bosons, they get quantized, or rather they are discrete in terms of either even multiple for pi over beta for bosons and odd multiples of pi over beta for fermions. So, these Fourier functions will be shown, these arbitrary functions f will be shown as the Green's function, and the merit of the Matsubara Green's function is that it directly leads to physical results such as the electrical properties such as conductance, or transport properties such as conductance, or magnetic properties such as magnetic susceptibilities, etc., and they are complex functions of I omega n, as you can see here. Now, if you need to go to 0 temperature, then one can do an analytic continuation. So, we will write this limit to 0 temperatures can be taken by analytic continuation of I omega n to omega n plus I eta. This is eta. So, eta goes to 0. So, you need to a plus or minus depend on whether we want to go to. So, this is for the retarded Green's function, and which are directly related to the experimental data. So, we have extended the 0 temperature formalism for an arbitrary function to finite temperature, and found that there are restrictions or conditions on the frequencies for bosons and fermions, and these show up in the form of poles of the Matsubara Green's function, and we shall now define the Green's function themselves. So, let us write down the Matsubara Green's functions. So, let us start with the electron Matsubara Green's function, but as we know that the only difference comes in the way the frequencies are quantized. So, we would only write down for the electron or the fermions. Let us write down for the use the word fermion rather than electron. So, the fermions we write it down for, but essentially you can write it down almost similarly, very similarly for the bosons as well. Here we will use a curly G, a calligraphic G to denote the Green's function and to distinguish it between with the 0 temperature Green's function. So, we have a 2 time involved and which is written as a minus T tau and a C k sigma tau and a C k sigma dagger tau prime. And so, now the 2 times are involved, or rather complex times are involved, and we have taken one k. One can take a k and a k prime and write the 2 operators, fermion operators with k and k prime. That won't change anything. Important thing is that we shall show that the Green's function identically depends on tau minus tau prime and not tau and tau prime individually. Thus, at the end one can drop one of the time indices and can write the resultant Green's function as a function of one time only. We will have to come to that. So, so let us write down k tau and tau prime. So, as we said that this will be written down in terms of the trace, and this T tau is again the time ordering operator which orders the time, that is earliest time tau, earliest tau to be closest to minus beta. Now, this is the difference between the 0 temperature Green's function, that we do not have a minus infinity here. The tau is bounded between minus beta to plus beta, which is why all these properties, symmetry properties of the bosons and the fermions came. So, we will write this once more, that let us before we write down the Green's function, let us at least define the T tau, a time ordering operator which arranges the fermionic operators such that the earliest tau closest to beta, closest to minus beta, is put at the extreme right. So, this is a definition of the time ordering operator, and so it serves the same purpose as the time ordering operator in 0 temperature formalism, excepting that that was pushed to minus infinity or plus infinity. Here it is pushed towards the one extremity, which is beta, or I mean minus beta in this particular case. So, we keep using the calligraphic Green's G for denoting Matsubara Green's functions. So, we have the left hand side is written with two time indices, the tau indices, we will see that how these two time indices can eventually be dropped. For that, let us write down k as tau prime. So, the time ordering can be trivially taken into account by the theta operators, which we have learned that tau is greater than tau prime, this is equal to 1, this function is equal to 1, else it is equal to 0, and trace of exponential minus beta k minus omega exponential tau k c k sigma exponential minus tau prime k. I will tell you what k is, and there is another term which is equal to, so this, and there is another term which is equal to tau prime minus tau trace of exponential minus beta k minus omega, all these k's omegas will be said just in a while, k, and then c k sigma dagger exponential tau minus tau prime k c k sigma exponential minus tau k. You should write this neatly and see for yourself. Now, this k is an operator. So, k equal to h minus mu n, where h is the Hamiltonian of the system, and we decide to work in the grand canonical ensemble. That is why this chemical potential has been used. Mu is the chemical potential, n is the number of particles, and this omega is called as the grand potential. And this grand potential is basically just like the free energy in canonical ensembles. So, the kT log z would give us a free energy, and this is actually the kT minus kT log z g, where z g equal to, just write it, where z g is the partition function in the grand canonical. So, this g corresponds to the grand canonical ensemble. So, remember that this is an operator while this is a scalar quantity, and this distinction will be needed in the subsequent discussion. So, now we shall use a theorem of the cyclic variation. So, it says that the trace is unchanged by a cyclic variation of the operators. That is, so trace of A B C is equal to trace of B C A is equal to trace of C A B, and so on. So, these are cyclically changing the traces, the trace remains invariant. So, what we why we say it is that we want to use the exponential minus beta tau term or exponential minus beta tau term, tau prime term, push it to the left, so that g k. There is another thing that has been achieved, is that the right hand side is completely a function of tau minus tau prime. So, we can start writing down the left hand side to be a function of tau minus tau prime, and this is equal to a minus theta tau minus tau prime. It is just mathematically a little cumbersome, but there is nothing very difficult about it. You have to just do it once by yourself to get convinced, and there is a trace that is there, exponential minus k exponential minus beta k minus omega exponential k this tau k, and then there is a c k sigma, I should have written it in one line, exponential minus tau prime k and a c k sigma dagger, and then there is this plus theta tau prime minus tau and trace and exponential minus tau k exponential beta k minus omega and exponential tau prime k and c k sigma dagger exponential minus tau prime minus tau k c k sigma. And so, these are the two terms where we have used the cyclic variation of the trace. Now, consider the commutation of these two operators. Now, there is the operator in these two terms, the two exponential are k only, because as I said omega is a scalar quantity. So, these two operators are both k, in the one is with the exponential minus tau k, the other is with minus beta k. So, they should commute. So, commutation says that exponential minus tau prime k exponential beta k minus omega and same with tau or tau prime, does not matter. In either of the terms, the first term there is a tau prime. So, we have written down here and exponential minus beta k minus omega and exponential minus tau prime k. So, these are the commutation and now we can use this commutation relation and can push the exponential k minus omega to the other side and write down the g as k tau minus tau prime minus theta of tau minus tau prime and the trace of exponential minus beta k minus omega exponential tau minus tau prime k c k sigma exponential minus tau prime k c k sigma dagger, and there is another term which is theta tau prime minus tau trace of exponential minus beta k minus omega exponential minus tau prime k c k sigma dagger exponential tau minus tau prime k c k sigma. So, that is the Green's function, and since as we have been saying that that depends upon tau minus tau prime on both the sides, drop one index, one variable rather. What did I? So, now that tells us that k tau is equal to minus t tau c k sigma tau and c k sigma dagger 0, because we are talking about just one time which is equal to minus trace of exponential minus beta k minus omega t tau of exponential tau k c k sigma tau c k sigma tau exponential minus tau k c k sigma tau 0 and so on. So, this is the form of the Green's function finally, which is what we have been trying to get at. It is a Matsubara Green's function, a function of I mean, we have taken this to be k, it could be any suitable quantum label for the problem. And now consider this additional symmetry properties that we have. So, consider tau to be between minus beta and 0, that means consider tau to be negative and use the property f tau to be minus f tau plus beta. We have been telling this that those arbitrary functions can actually be like our Green's functions, which are relevant for us, and in this limit of minus beta less than tau less than 0, then we can write down the g k tau to be equal to trace of exponential minus beta k minus omega and c k sigma dagger exponential k c k sigma exponential minus tau k, and that is the form of the Green's function. And now, one can use that cyclic property of trace several times and can write it down as, so we will write this, give this clue here, use cyclic invariance of trace g k tau equal to trace of exponential beta omega exponential beta tau k c k sigma exponential minus tau plus beta k and c k sigma dagger and so on, so exponential beta omega is not recycled because it is not an operator. Recycled means it is not just the way the trace of ABC and BCA, that it has not been done, it has been kept where it is, it has not been recycled. And then finally, I mean, one can do a regrouping by adding adjusting exponential plus minus beta k, we have written down as g k tau equal to trace of exponential minus beta k minus omega exponential tau plus beta k. Remember, k equal to h minus mu n. So, this is our Hamiltonian now, and this and then c k sigma exponential minus tau plus beta k c k sigma dagger, and so this is the form of the Green's function. And the term so the term in the right, that is this term, is equal to nothing but equal to minus g k tau plus beta for we have taken that from 0 less than tau less than or rather minus beta less than tau less than 0. And so, this is the property that we were talking about, and so this equality is satisfied by, as the same equality was satisfied by the function, the arbitrary function that we had talked about, and the this above identity this allows the Green's function to be expanded in a Fourier series of the type that g of k I omega n equal to 0 to beta d tau exponential I omega n tau and g k tau and the g k tau is written as 1 over beta sum over n exponential minus I omega n tau and k I omega n. So, these properties are exactly same as that arbitrary function with omega n to be odd multiples of pi over beta. So, your I omega n are odd multiples of pi over beta. So, this is formally representing the Green's function, the Matsubara Green's function. We will do some examples with this, and let us do one example, and let us write down example. So, we write down the non-interacting Green's function, Matsubara Green's function, non-interacting Matsubara Green's function. Okay, so H equal to H0, which is equal to sum over k epsilon k c k sigma dagger c k sigma. Now, here k is same as k0, which is same as H0 minus mu n, which is a k and a sigma, and we have a xi a k c k xi k c k sigma dagger c k sigma, where this xi k is nothing but epsilon k minus mu. So, the tau evolution of the operators can be written as is that the c k sigma tau it's equal to exponential k 0 tau k 0 and the c k sigma exponential minus tau k 0. We just proved this in a while, and this is equal to minus psi k tau c k sigma. So, this is the tau evolution. Tau is, remember, tau is complex time. So, the tau evolution of these are like this, and similarly the tau evolution of the creation operator is like this. And this can be proved using what is called as the Baker-Hausdorff theorem. Which says that exponential a c exponential minus a equal to c plus a c plus 1 by 2 factorial a c and 1 by 3 factorial a c and so on. So, this can be applied to our case, where we have an exponential tau k 0 c k sigma and exponential minus tau k 0. This can be written as C k sigma plus tau k 0 C k sigma and plus so on, and tau psi k, which is k 0 is h 0 minus omega n. So, k 0 is equal to sum over k psi k C k sigma dagger C k sigma, where so this is a tau psi k will come out, and I will have a C k sigma dagger C k sigma with C k sigma, which is simply equal to tau psi k C k sigma. C k sigma, and hence we can write down a C k sigma to be equal to C k sigma minus a psi k tau C k sigma plus a psi k tau square by 2 factorial C k sigma and so on, and this can be actually written down as an exponential tau psi k C k sigma and so on. So, that is how we can write down the Green's function for the non-interacting problem, which for which I have introduced this 0 and this is written as a minus theta of tau and exponential minus psi k tau and a C k sigma dagger C k sigma and plus the other term theta tau exponential minus psi k tau C k sigma dagger C k sigma. We have written it somewhat sloppily, it has to be here and so on, and this can be written as exponential minus psi k tau and a theta tau 1 minus nf psi k. We have shown that this is equal to, this angular bracket is equal to 1 minus nf and theta of tau to be, or minus tau to be here, there is a minus tau here, which is nf psi of k. So, the two combined, so nf is nothing but equal to nf of psi k is nothing but a C k sigma dagger C k sigma, which is equal to 1 divided by exponential beta psi k plus 1. It is easy to obtain the frequency dependent Green's function, which is equal to k and I omega n, which is nothing but a 0 to beta d tau exponential I omega n tau g 0 and a k tau minus 1 minus nf 0 to beta d tau exponential I tau omega n minus psi k, and this is written as 1 minus of 1 minus nf and exponential beta I omega n minus psi k minus 1 divided by I omega n minus psi k. Remember that the second term in the numerator here can be simplified if we use exponential I beta omega n to be equal to minus 1 for I beta n to be 2n plus 1 I pi, and then I can write down the Green's function, the 0th order Green's function, as k I omega n, which is equal to 1 minus nf exponential beta minus beta psi k plus 1 divided by I omega n minus psi k, it is equal to I omega n minus psi k, because my 1 minus n f equal to exponential minus beta psi k plus 1. So, the temperature information is encoded in the frequencies omega n. So, now as we said that the 0 temperature result would be obtained by analytic continuation of I omega n going to omega n plus I eta to the real axis, and in the so in the same spirit as the 0 temperature, the plus sign would relate it to a retarded Green's function, and the minus sign would be an advanced Green's function. So, this is how the 0 temperature limit is taken from the finite temperature. And the reason that the 0 temperature limit is relevant is that because the benchmarking temperature scale in fermionic system is given by the Fermi temperature, and the Fermi temperature for metals it is of the order of 70,000–80,000 Kelvin. So, even a temperature which is room temperature 300 Kelvin can be taken as 0 temperature. So, sometimes in fermionic systems we may need, or we can get by with the 0 temperature properties or 0 temperature formula that is relevant even when the temperature of the system is, or the experiments are done at room temperature.